Hi and welcome to another video tutorial. In this video tutorial I'm going to be going through how we represent sound in digital form. So sound waves, when they're produced, are analog. So we must convert them to a digital format if we want to store and process them on a computer. The process we use to convert analog sound waves into a digital format is called sampling. Okay, so let's go over that again. Sound waves are, when they're produced, are analog. So we need to convert them to a digital format to store and process on a computer. We use sampling to achieve this. So let's go through what I mean by sampling and two key terms that you need to know about when we refer to sampling, and then I'll go through an example. So sampling is where we take a measure of the amplitude of a wave at regular intervals along the wave. So when a sound wave is sampled, we take a measure of the amplitude of the wave at regular intervals. So there's two key terms you need to know about when we're talking about sampling sound. You need to know about what the sampling rate is and what the sampling resolution is. Let's deal with the sampling resolution first. So the sampling resolution is the number of bits we use to store each sample. And increasing the sampling resolution increases the number of different amplitudes that can be represented, and therefore allows a sample which is closer to the true waveform that we're trying to represent. So if you're asked what the sampling resolution is, it's the number of bits used to represent each sample. So let's now move on to looking at sampling rate. So the sampling rate is quite simply the number of samples that we take per second. In my example over here, this graph covers a time period of 2 seconds. I might take 3 samples every second, so that would be my sampling rate, 3. And it's usually measured in hertz, so increasing the number of samples taken will increase the accuracy of the waveform that we're storing. So how close the digitally represented waveform is to the original analog wave. So if you're asked what the sampling rate means, it's the number of samples taken every second. So let's take a look at closer look at this graph over here. The black curved line is my analog wave, and the red line is what my digital representation of this wave is going to be when I sample it at a 2-bit sample resolution. And the reason this sample resolution is 2 bits is because we've got 4 different states essentially that we can that the amplitude can be. So 4 discrete values that the amplitude can be. So we've got 0, 1, 2, 3 over here, and if we need to represent 4 values, we need 2 bits to do that. 2 bits can represent up to 4 values. So let's say, for example, that I took 4 samples every second. So I've drawn on some black crosses where I would take my samples every second. And you can see that my first sample is taken here, so I would record however we're representing. If we're representing it with 2 bits, our binary would be 0, 1, like that. So I would that would be my sample there, and then I sample the wave here, sample the wave here, sample the wave here, sample it here, 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 and here, where my black crosses are. And you'll notice that these black crosses are the same distance apart, so we're sampling it at a regular interval. Regular time interval. So if we're sampling it 4 times every second, we'd sample it at 0.25 seconds, 0.5 seconds, 0.75 seconds, and 1 second. And because we're doing that, the sample might be the same as the last one. So here I've sampled it here, and we're at a value of 3 on our amplitude axes here. I sample it 3 more times before the first sample where it's actually changed. And that's just because we're sampling it at a regular interval. But you can see that if I increase the number of discrete values that I could sample at, so increase my sample resolution, this red line here, which is my digitally stored wave, would be much closer to the original waveform than it is at the moment. And I'm only using a 2-bit sample resolution here, but when we're actually storing digital sound in the real world, we would use a much larger sample resolution than this. I think CDs use a 16-bit sample resolution. Okay, so that's an example of what it would look like to try and sample some sound. The last thing you need to know about is how to calculate the size of a sampled sound file. So how to calculate how many bits it would take to represent this wave. And this is the general formula. So the file size, bits, is given by the sampling rate multiplied by the sampling resolution multiplied by the length of the sound file in seconds. So we could roughly work it out for what this wave would be on our graph axes here. Our file size would be our sampling rate, which is 4, multiplied by our sampling resolution, which is 2, multiplied by the length of the sound file, which is 2, which gives us 16 bits. Okay, so that brings us to the end of this tutorial video. I hope you found it useful, and I'll see you in the next one.